number 72, benzene has the formula C6H6 is a planar compound in which the carbon atoms are arranged in a hexagon, six-sided polygon. The Lewis diagram of this molecule is a geometry that accounts for the observed shape of the molecule, including bond angles. Draw this diagram. Experimental evidence shows that the diagram does not describe the structure of benzene accurately. All right, so they're telling us that it's a ring structure. So if we look at C6H6, how many electrons do we have? So we got 6 carbons, 6 times 4 is going to be 24 electrons. We've got 6 hydrogens. So altogether we have 30 electrons. Now, the way we're going to link the carbons is we link it so it forms a 6-sided polygon like this. So that's the way it would look. And then what do we do with the hydrogens? Where would we put the hydrogens? Well, the only place they can go are on the carbon, so we'll just put 1 hydrogen on each carbon, like this. So how many electrons does that take care of? Just count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've done 24 electrons, you know, out of the 30. So we need to complete the octets though. So we could try completing the octets. You know, carbon would need 2 more electrons to complete the octet. So each carbon needs 2 more electrons. This, then we have an octet. But, you know, we've used 24, so this would be 26, 28, 30. We don't have enough electrons to complete the octets, everybody. In fact, we only have 6 electrons left over, so I can't complete the octet. The best I can do is I can just give 1 electron to each carbon. But if I give 1 electron to each carbon, then it's going to be less than an octet, so it won't be so happy. But is there something else I can try to do? I'm sorry? I can't put 2 hydrogens. I only have 6 hydrogens. If I did it, then it would work out. But in this case, I think you
Double bond all the carbons?
yeah. If I double bond, I can't double bond all of them because to create a double bond, you know, requires 2 electrons. So what I can do is I can do this. Do this. Just drop an electron. Drop an electron here and here. So we share these rather than have these individually. And so I'll put a double bond here. Then I'll put a double bond here. And then I'll put a double bond here, like that. And so in that way I can complete the octet. So I'll end up with a situation that's going to look like this, where we're going to have alternating double bonds. These alternating double bonds are going to make it work out so that everybody has an octet. Here, like that. And so when I look at this, look, this carbon has an octet 2, 4, 6, 8. 2, 4, 6, 8. Every carbon has an octet, you know, surrounding it. So this is it. However, why did I choose this? Did you see, why did I choose this bond here? I could have chosen this bond here to make the double. You see, I just take this one and then share them. And it turns out that, yeah, sure, I could have done that. And if I did that, I would have gotten a resonance form that looks like this. Here. So this accounts for the shape. So when we look at this, what's the electron pair geometry? What's the EG for this? Electron geometry for this carbon. Not tetrahedral. How many groups do you count?
Trigonal plane.
Trigonal planar. One double bond, two single bonds, trigonal planar. Trigonal planar is going to be 120 degrees, correct? But we expect distortions here because of the double bond. But the funny thing is these angles are not distorted. All these angles are 120 degrees because the true structure is not this one nor this one. The true structure is I have two resonance forms for this. The true structure is more of a resonance, starts with an H. Hybrid, right. And so what would the hybrid structure look like? The hybrid structure is going to be an average of those two. So if I average those two structures, then there's going to be a single bond fixed on each carbon, like this. But the double bond is going to be spread out. What did I call that when it's spread out? There's a word for it that started with a D. What's that? It starts with a D and ends with a D. A word. It's like what happens to water, you know. Water spreads out, fog spreads out, electron cloud spreads out. We call it, rather than being concentrated or localized, we call it Nobody wrote it down? Yeah, that's... It's hard to catch. This is why, you know, and this is something I recommend. This is why I love to record things if possible, because then it's easier to miss it. But it's called delocalized, and so we delocalize the electrons like this. And so all the bonds are the same. Rather than being a single and a double, they end up being 1.5. And so this is very symmetric. This is going to be 120 degrees. There are different ways that people show this delocalization of electrons in benzene. A lot of people, this is the shorthand symbol for benzene, and to show the delocalized double bonding electrons, they draw a ring in the center of it. And so that's the symbol for benzene. It shows it. Let's see what they did. They did this. Of course, neither of these, because we have two resonance forms. And so it says, this structure does not describe the structure of benzene. This is a much more accurate description of the structure of benzene. All the bonds are the same. That's what we end up with. Okay, any other questions? Well, speaking of drawing structures, let's just draw glycine out really quick. You know, for glycine, you know, the NH2 is a tetrahedral electron geometry with 3 single bonds and a lone pair. Normally with the single bonds in the plane, but in this case, for glycine, this is glycine. I like to put the lone pair in the plane and this one single bond in the plane. Then it's an NH2, so there are 2 hydrogens bonded to that. this is bonded to a CH2. And so what we want to do here, and some people did this, they flipped it the opposite way. Do you see, if this is tetrahedral 2, we'll put 2 in the plane, and the one coming out, and one going in. But we want to orient it the same as this. So one coming out to the right, and one going in to the left here. This is a CH2 here. So we want to look at it from the same kind of angle or the same kind of perspective here. So this is why I just want you to be aware. You don't want to flip this because then we're looking at it from 2 different angles. What I mean by flipping it is some people had it flipped the opposite way, where the one coming out is now on the left and the one going in is on the right, but that's a different perspective than this. Does that make sense? You keep a consistent perspective. And then this goes to, this is tetrahedral EG. What's the MG for this? Trigonal pyramidal. And so the reason I drew it like this is I wanted to show the trigonal pyramidal kind of shape to this, the triangular pyramid here. The lone pair is here, but if we ignore the lone pairs, then we got this. I mean, you could have put in 2 bonds, in the plane, and the lone pair sticking out or sticking in, but you'd be a trigonal pyramid, but tilted on its side. So this is kind of why I drew it like this in class. Then this one. Now, for lone pairs on central atoms, I want you to show me what's going on with the lone pairs on the central atom. But for terminal atoms, you don't necessarily have to show me what's going on with the lone pairs for the terminal atoms. The terminal atom would just be like this, this oxygen double bond here would be a terminal atom. Some people showed me what's happening because I have 3 ways of drawing lone pairs. If I drew the lone pair like this, what does that mean? It's sticking out. If I dotted them like this, it's sticking in, and if I just drew them as circles, it's in the plane. And so if I look at this oxygen, which is a terminal atom, what's electron geometry of this oxygen here? Trigonal planar is correct. If it's trigonal planar, does that mean it's flat, or does that mean it kind of sticks out, projects out? It's flat. And so what some people did was they made the lone pair stick out or stick in. So it's tweaked a little bit. Both of these lone pairs and this double bond should be in the same plane. That's a terminal atom, so not really going to deduct if you drew the wrong shape around that. But this oxygen, however, is a bridging oxygen, or central oxygen here, because it bridges these 2 atoms here. So it's at the center of these 2 atoms. Here I need to see what's happening with the lone pair. So there's 2 lone pairs here and 2 bonds, so it'd be tetrahedral. So that means I need to draw 1 lone pair sticking out if I want the bonds in the plane, which I do, and then 1 lone pair sticking in. And so I'll draw it to the same perspective as this. On the right I have something sticking out, on the left I have it sticking in. Do you see that? This is tetrahedral, this is tetrahedral, this is tetrahedral. Although this is a tetrahedral electron geometry, its molecular geometry is not. What is the molecular geometry of this? Bent. And the angle should be 109.5, but it's going to be distorted a little bit down to about 105. These angles, but actually we could do the angles here. The angles for nitrogen here, this should be 109.5 because it's tetrahedral, but it's going to be distorted because the lone pair is about 107. This one should be 109.5, should be distorted. This one's going to be distorted. Like, for example, this angle is going to be a little bit bigger. This angle is going to be a little bit bigger. What did we say, roughly? Yeah, this one should be 116. We got to add up. This is going to be about 122. This is going to be about 122. Because of the double bond takes up more space. This one's going to be stored at about 105, roughly. These are going to be 109. This is going to be about 107. 109. 109, 109.5, like that. You know, the ideal angles for this would be 109.5. This one should be 109.5 degrees. This should be 120 degrees. This should be 109.5 degrees. But we expect some distortion. And so those would be the ideal angles. And then again, EG for this is tetrahedral. T sub G, MG is trigonal pyramidal. EG for this is tetrahedral. MG is tetrahedral. EG for this carbon is trigonal planar. And this oxygen, MG is trigonal planar. And this oxygen, EG is tetrahedral, MG is bent. And then the ideal angles are given here in black. Distorted angles in blue. All right, any questions on that? All right, another thing I notice with people on the quiz is that, I don't know if people aren't getting it, but formal charge. How do you calculate formal charge? Actually, how many people feel comfortable with formal charge? All right. For those of you who feel uncomfortable about formal charge, there's different ways to calculate it. We could look. For example, this is a very common way. This is the way I learned how to calculate it when I was taking chemistry. The formal charge is equal to the number of valence electrons minus the number of non-bonding valence electrons minus the number of bonding divided by 2. So if you don't like the way we did it in class, you can always use this formula to calculate the formal charge. And so let's try this formula out here. So for example, H2O. Let's do some simple ones. If I look at H2O, I want to do the formal charge on hydrogen. So the formal charge is equal to B minus N minus B over 2. Okay, so how many valence electrons does hydrogen have? 1. And then N is the number of non-bonding valence electrons. Well, number of non-bonding valence electrons, do you know what that means? That means number of lone pair electrons. Lone pairs are not bonding with anything. And so how many lone pair electrons does hydrogen have? 0. So minus 0. Minus the number of bonding electrons divided by 2. How many bonding electrons does hydrogen have? It has 2 bonding electrons divided by 2 is 1. And so the formal charge on hydrogen is 0. Okay. Let's take a look at oxygen next. Okay, the formal charge is equal to, how many valence electrons does oxygen normally have? 6. Okay, minus the number of non-bonding electrons. 1, 2, 3, 4. Minus the number of bonding electrons divided by 2. How many bonding electrons? 1, 2, 3, 4. 4 divided by 2. And so So 4 divided by 2 is 2. 6 minus 4 minus 2 is 0. So the formal charge is 0 on all of those. Is this better, you say? Okay. Let's take a look at another one here. As an example. You know what this is called? What's that called? Hydronium. This is a hydronium. So let's do hydrogen first. The formal charge is equal to the number of valence electrons. How many valence electrons does hydrogen have? 1. Minus the number of lone pair electrons? 0. Minus the number of bonding electrons divided by 2? 2 divided by 2. The formal charge on hydrogen is 0. Let's go to oxygen next. Formal charge is equal to the number of valence electrons on oxygen, 6, minus the number of lone pair electrons or non-bonding electrons, 2, minus the number of bonding electrons divided by 2. So how many bonding electrons on oxygen? 2, 4, 6. 6 divided by 2, 3. So this comes out 6 minus 2 is 4, minus 3 is 1. And so that means oxygen has a formal charge. Now, formal charge we circle. Oxygen's formal charge is plus 1. We just write as plus, like that. 0 formal charges, we don't bother. See that? Okay. Let's try this one next here. Okay, hydrogen's formal charge should be the same, but what's oxygen's formal charge? Hydrogen should have 0 because you see it's going to be the same. Yeah?
Look at oxygens.
Yeah, let's take a look at oxygen's formal charge. The formal charge is equal to valence, which is minus the number of non-bonding electrons.
6.
2, 4, 6. Minus the number of bonding electrons divided by 2. Divided by 2 is 1, minus 1. The formal charge on oxygen is?
Minus 1.
Minus. This is hydroxide. What's this called? Oxide. And so let's look at the formal charge on oxygen here. 6 minus what? 8 minus 0 divided by 2, which is 0. So 6 minus 8 is negative 2. And so formal charges we circle, and it would be negative 2 circled like that. Why do we need formal charges? We need formal charges to try to figure out what the most stable Lewis structure might be. So let me give you an example of that case here. Example would be like let's look at this. Versus this. Okay, can you calculate the formal charge on the both the structures? Well, first, are both those structures okay? Do we have an octet? Do we have octets? Are there octets? Yeah, on this oxygen, there's an octet 2468. This carbon, 2468. This octet. This carbon, 2468. This oxygen, 2468. So both of those have an octet. So, so which one do you prefer, the left one or the right one?
The left one,
Why?
because the other one has a +2 charge.
Okay. Yeah, because of formal charge. That's why. The left one is much better. Can you calculate the formal charges on these here, and then tell me what you get? Everybody. If you can't, then let me know and I'll help you with the formal charge.